We're going to cover entropy in this video. This is the second part of before thermodynamics. Now, entropy is basically a measure of disorder in a system. There are two main interpretations of entropy. One is on a micro level, and we examine this through something called microstates. Now, to start easy, so let's say we have a container of particles, and so let's say for a particle, we can describe its microstate as A, B, or C. It could be A, it could be B, or it could be C. So for this particle, there are three microstates. Then for another particle, we can say the same thing. And for another particle, we can say the same thing. So there are 3, 3, 3. And so if you learn some basic combinatorics, you would learn that this gives a total of 27 microstates. So entropy is often can be measured with the number of microstates. So the exact formula is it's the product of the Boltzmann constant and the natural logarithm of the number of microstates. For a real physical object, or liquid, or gas, or solid, each microstate is basically consists of a position and a momentum. So these things would make up microstates. Then if you think about the whole thing, so this omega, it's basically equal to the number of possible microstates for one particle times the number to the power of the number of particles. So if you think about, let's say, if we increase the volume, then that would greatly increase the number of possible positions, and it would greatly increase this. If you increase momentum through, let's say, increasing the temperature, which allows the spectrum of velocities to increase significantly, you're also increasing the number of microstates for each particle. So then each of these actions would increase the entropy, as we would say. So another way to consider this is through a macro perspective. And this is through a series of derivations from the micro definition. Find that the change in entropy is equal to the change the heat transfer over the temperature at which this is done. So then we would find that in the whole universe, if we take the whole universe as a system, we would see that entropy only increases. And that is the second law of thermodynamics. It's basically that the measure of order and chaos always increases. You might be able to say, let's say by freezing water, I can decrease its entropy, but considering the system that does, or another part within the system of the universe that does this to it, that its entropy would increase. So then the net entropy of the universe would always increase. One way you could convince yourself is you can consider mixing water at T1 and T2. You can calculate the respective entropies for each of the water, each component of water, and then you can add them up to see that it is going to be positive. So this is like a very basic experiment you could do. If you look at entropy as a whole, though, it is a certain irreversibility. I think that is the best way to say it. It is irreversible, and therefore it predicts an ultimate fate of the universe of heat death. Basically, the idea that ultimately everything is going to have the same temperature, is going to be one soup of the same thing. So that, I think, is entropy summarized.